You know when you're typing out a really fast text message and your phone autocorrects something completely normal into, like, absolute nonsense?
Oh, yeah, constantly.
Right. Like you try to text your boss, "I'm arriving now," and your phone just decides to send, "I'm a ravioli now."
A ravioli.
Yeah, and you just hit send without even thinking twice. And, well, for a long time, that is basically how we've been building our most advanced artificial intelligence. They're just these massive, incredibly fast autocorrect engines.
Exactly, just guessing the next word.
But today, we're looking at a state-of-the-art foundational paper that actually teaches AI how to hesitate. What if they could pause, look at the text, realize, hey, wait, I am not a ravioli, and fix it before hitting send? So our mission for this deep dive is to explore a massive leap forward in agent intelligence. Specifically, we're looking at a new framework called Reward-Driven LLM Agent Workflows, or RL-LOLI. We are diving into how AI is evolving from a system that just blindly guesses the next word to one that actually thinks twice.
Yeah, and we are also looking at some hard data today that honestly challenges everything the industry thought it knew about size. This paper demonstrates how a smaller, deliberately slower AI model is completely obliterating much larger, faster models in these complex real-world tasks.
Okay, let's unpack this, because to really appreciate the solution, we have to understand the problem first. So I want to start with what is currently considered, the standard for AI agents. The paper mentions something called the REACT framework. Why are current agents failing when we ask them to do complex things?
Well, the fundamental problem really stems from the architecture of large language models themselves. Like you mentioned with the autocorrect analogy, standard LLMs are generative. They operate on a principle called maximum likelihood estimation.
Which sounds super technical.
Right, it sounds highly technical, but it simply means the AI is looking at all the text it has ever been trained on and mathematically guessing the most popular next word based on that past data. It doesn't actually understand the overarching goal.
Got it. So even if I ask, say, a standard React agent to do something complicated like navigate a web browser to buy a specific pair of shoes, or, I don't know, control a robotic arm to make coffee,
Right.
it is still fundamentally just playing a really high-stakes game of fill in the blank.
That is exactly the illusion of current AI reasoning.
Yeah.
I mean, the REACT framework, which stands for Reasoning and Acting That Might, was an early attempt to fix this by forcing the AI to write out its thoughts before taking an action. It interleaves reasoning traces with its commands.
Okay.
But underneath it all, it still lacks a formal, mathematical, objective function. It doesn't have a goal-oriented brain. So when you put that kind of agent into a dynamic, unpredictable environment, that limitation becomes fatal. The agent suffers from what researchers call cascading hallucination errors.
Cascading hallucination errors. Okay, so it's like trying to bake a cake, but you accidentally use salt instead of sugar in step one.
Yes,
It-
yeah, exactly.
Because the AI has no taste buds to check its work along the way, it just blindly keeps adding ingredients, following the recipe to the letter. It thinks it's doing a great job until the whole cake comes out of the oven completely ruined.
What's fascinating here is that the AI cannot recognize its own intermediate failures.
Mm.
A single illogical assumption early in a reasoning trace just derails the entire execution pathway.
Mm.
Without those internal taste buds, the AI cannot evaluate an action until the environment violently pushes back.
But wait, hasn't the AI industry already tried to fix this by just, throwing way more computing power at the problem? We keep hearing about these massive 70 billion parameter models or 100 billion parameter models. Doesn't sheer size and a bigger vocabulary eventually solve that hallucination problem?
Raw size absolutely does not fix a fundamental lack of mathematical objectives.
Mm.
A larger model is essentially just a more confident guesser. Yeah, the researchers show that bigger standard models still fall into infinite execution loops, or they try to do completely physically impossible things. Scaling up the parameters gives the AI better grammar, sure, and a wider array of facts to draw from, but it doesn't give it common sense. It doesn't give it the structural mechanism required to realize it is about to make a catastrophic error.
Which means we need a totally different architecture. And I guess that brings us to the RLAW paper. How does this new framework fundamentally rewire the AI's brain to give it those taste buds?
It takes generative AI and fuses it with a completely different branch of machine learning called reinforcement learning.
Okay.
See, generative AI is great at being creative, but reinforcement learning is strict. It's mathematical and purely driven by rewards and penalties. So RLA structures the AI's interaction with the world using a POMDP, that stands for Partially Observable Markov Decision Process.
Partially observable. I imagine that is like trying to navigate a dark room. Like you might know you are generally in a kitchen, but you don't actually know what is inside a specific drawer until you physically go over and open that drawer.
That captures the core challenge perfectly. The true state of the world is hidden. And because the AI cannot see everything at once, it has to build and maintain a belief state based on its history of actions and observations.
Right.
To manage this belief state without getting totally overwhelmed, RLAW introduces a strict three-phase loop: propose, critique, and execute.
Okay, I want to break down those three phases mechanically, starting with phase one, which is the actor. This is the generation phase, right?
That's right.
So the AI looks at its goal, looks at its memory, and proposes an action. But the paper emphasizes that the actor uses something called graph memory. How's that different from how an AI usually remembers things?
Well, normally, an AI agent relies on a flat text log. It just reads a giant running transcript of everything it has done so far. Like, I walked to the kitchen, I opened the fridge, I saw an apple.
Yeah.
Over a long task, that transcript becomes massive and incredibly difficult for the AI to parse.
Yeah, that sounds like a nightmare to read through.
It is. So graph memory changes that by building a semantic scene graph. The RLI agent mathematically represents spatial relationships using nodes and edges.
Meaning it creates a mental web, like it maps out that a key is a node, and it draws an edge connecting it to the drawer node, which is then connected to the kitchen node.
Exactly. It is dynamically updating a structural blueprint of its environment. It doesn't have to reread a 10,000-word log just to remember where the key is. It just queries the graph. This allows the actor to propose highly contextual, logical actions.
So the actor proposes an action based on that graph memory. Now we hit phase two, which, reading through this, is the absolute secret sauce of this entire framework, the critic.
The critic is brilliant. It's a secondary, highly specialized, lightweight neural model living inside the broader system. Its entire job is to intercept the actor's proposed action and evaluate it against the overarching semantic goal. It acts as an internal reward mechanism.
But hold on. If the critic is just another AI model who critiques the critic, doesn't this just push the hallucination problem one layer deeper? Like, why should we trust the critic's judgment more than the actor's?
Because the critic is trained differently. While the actor is trained on massive data sets to generate open-ended text, the critic is trained specifically on trajectory data.
Trajectory data.
Yeah, examples of successful and failed actions in specific environments. It isn't trying to be creative at all. It is running a strict logic check. Like, is this action physically possible? And a safety check, will this cause an infinite loop? It then outputs a continuous scalar score between 0 and 1. If that mathematical score falls below a strict threshold, the critic outright rejects the action.
Here's where it gets really interesting. This mathematical threshold is exactly what psychologists describe in humans as System 2 slow thinking.
Oh, exactly.
Daniel Kahneman wrote extensively about this. System 1 is our fast, automatic, impulsive brain. That is the standard LLM blurting out the first mathematically probable answer. But System 2 is our slower, deliberate, analytical brain that double-checks the math before we actually speak. By using this critic, we are literally teaching AI how to hesitate, self-reflect, and run a diagnostic on its own thoughts.
It is a remarkable convergence of cognitive psychology and mathematical architecture, which brings us to phase 3, execution. Only if the action passes the critic's strict threshold is it actually executed in the external environment.
And if it fails?
The action is blocked. But more importantly, the critic generates natural language feedback explaining why it failed, and it forces the actor to regenerate a new idea.
That sounds incredibly powerful in theory, but how does this internal critic actually play out when an AI is about to make a physical mistake? Because, knowing you are wrong in abstract math is one thing, but knowing you are about to mess up a real-world task requires a totally different kind of reasoning. The paper has a case study on this from a simulated physical environment called ALF World. What exactly is ALF World?
So ALF World is a highly complex embodied text environment. It requires an AI agent to navigate a simulated house, find objects, and manipulate them to solve a puzzle. The specific tasks the researchers highlighted to show the difference between standard AI and RL was this: find a clean sponge and place it on the vanity table.
That sounds simple enough for a human. You just, find a sponge, wash it in the sink, and put it on the table. When the researchers tested the standard mainstream React model on this, how did it handle the sequence?
It failed almost immediately. Yeah. The React agent navigated to the bathroom, found a dirty sponge in the sink, picked it up, and slapped it onto the vanity table. It achieved the physical movement, sure, but completely ignored the semantic constraint that the sponge needed to be clean. The simulated environment instantly registered the task as a failure.
Because it just guessed the next logical word sequence, take sponge, place on vanity without a System 2 critic to intercept the bad logic. Walk us through the exact trajectory of how the RLAW model, facing the exact same scenario, handled the dirty sponge.
Right, so the RLAI actor navigates to the bathroom and sees the dirty sponge. Just like the standard model, the actor's first instinct is to propose the most statistically common action, which is take dirty sponge from sink.
Okay.
But before it is allowed to interact with the environment, the critic intercepts that proposal. The critic evaluates the action against the ultimate goal, realizes the goal strictly requires a clean sponge, and assigns the action a failing scalar score of 0.35.
Wow. That stops the AI from actually picking it up. But you mentioned earlier that the critic doesn't just block the action, it gives feedback. What does that feedback look like?
It generates a natural language diagnostic for the actor. It essentially tells its internal system, the sponge is dirty. You must turn on the faucet to clean the sponge before taking it. The actor receives this feedback, generates a new action to turn on the faucet, washes the sponge, takes it, places it on the vanity, and successfully completes the task.
If we connect this to the bigger picture, the value isn't just that the sponge got washed. The value is that the AI caught its own bad idea before it touched the external environment. If I understand the paper correctly, keeping the external environment pristine is a huge deal for an AI's memory.
Oh, it's massive. That moment of internal interception is revolutionary for context management. See, in standard models, if the AI makes a mistake, it actually executes the action. The environment then spits back an error message like invalid command or nothing happens.
Yep.
That error message gets permanently added to the AI's context window. As the AI keeps trying and failing, its memory becomes incredibly cluttered with error messages. It gets confused by its own failures and spirals into an endless loop. By filtering out bad actions internally, RLAW prevents that domino effect of hallucinations from ever starting.
But an anecdote about an AI washing a simulated dirty sponge is one thing. When we look at the hard data, does this slow-thinking approach actually hold up across thousands of complex interactions?
The paper provides extensive empirical evidence across 500 evaluation episodes, and the numbers are honestly staggering. On that ALF world simulation, the RLAI architecture achieved a 78.6% absolute success rate.
Let's put that 78.6% in perspective. What did the standard React baseline score on the exact same 500 episodes?
The React model scored just 54.1%, and the zero-shot base model scored a dismal 22.4%.
For those listening who might not be deep in the machine learning weeds, what does a zero-shot base model mean?
Zero-shot means asking the underlying language model to solve the problem completely cold, without any prior examples, warm-up tasks, or iterative reasoning loops. It is just the raw LLM trying to predict the entire solution in one go. Its 22.4% success rate shows just how difficult the environment is without a deliberate workflow.
So RLAW is crushing the standard models in sheer success. But what about the hallucination rate? Did the critic actually do its job of stopping the AI from trying to execute impossible or nonsensical actions?
Drastically. The hallucination error rate for the base model on ALF World was 45.1%. Nearly half the time, it was trying to do things that defied the physics of the simulation.
Half the time.
Yeah, but RLAW pushed that hallucination rate all the way down to just 12.4%. They also tested this on a totally different data set called WebShop.
What's that?
WebShop forces the AI to navigate a massive real-world e-commerce website with over 1 million products, searching for specific items with complex attributes. RLA achieved a 65.8% success rate there, compared to React's 42.3%.
Okay, the success rates are undeniably better. The hallucination rates are dropping. But, I mean, there is always a catch. Running an AI that runs a secondary AI inside its own head to constantly check its math sounds incredibly computationally expensive. Didn't this take a massive supercomputer to pull off?
This leads us to the single most shocking revelation in the entire study. The researchers tracked the scaling laws, meaning how does the sheer size of the model impact its performance. They pitted an 8 billion parameter version of their RLI model against a massive 70 billion parameter version of the standard React model.
8 billion parameters versus 70 billion. That is a massive David versus Goliath scenario.
And David won.
Wait, really?
Yes. The 8 billion parameter RLI model explicitly outperformed the 70 billion parameter standard React model across these complex tasks. It achieved a higher success rate with roughly 1/9 of the raw parameter count.
That completely flips the script on how we build AI. How does a model that is 9 times smaller actually win?
It proves that architectural ingenuity beats raw brute force computing power. The 70 billion parameter model is using all its size to memorize a massive vocabulary and vast amounts of world knowledge. But because it doesn't have an internal critic, it applies that knowledge clumsily.
Right.
The smaller RLAW model might know fewer arbitrary facts, but it is using its parameters to strictly evaluate its own logic. It turns out that teaching a model how to think is a far better use of compute than just giving a model more things to memorize.
So what does this all mean? If RLO is this much more accurate, eradicates hallucinations, and can achieve state-of-the-art results on significantly smaller models, why isn't every single AI company implementing this exact architecture today? What are the actual trade-offs of forcing an AI to hesitate?
The cost of System 2 thinking is measured in latency, power consumption, and memory overhead. Thinking takes time. The researchers profiled the hardware utilization on a standard consumer-grade GPU. They looked specifically at the tensor cores.
Tensor cores being the specialized math engines inside the graphics card that handle all the heavy lifting for neural networks.
Precisely those. Because RL is constantly proposing, mathematically critiquing, rejecting, generating natural language feedback, and regenerating actions, it requires sustained utilization of those tensor cores. The paper found it takes the RLN model 2.15 seconds to generate a single step in the environment. The standard React model, which just blurts out its first guess, takes only 1.20 seconds.
So it's nearly twice as slow, and I imagine running those math engines that hard for that long creates a power issue as well.
It does. RLN draws 210 watts of power during operation compared to React's 180 watts. But the biggest constraint is actually memory. We talked earlier about how RLL maintains that persistent graph memory of the room. It also has to maintain the history of all the times the critic rejected an idea so it doesn't repeat the same mistake.
Right.
Because of all this internal monologuing, the context window fills up incredibly fast. The paper noted RLAgobi consumes about 3,500 tokens of memory per reasoning step.
If a task takes 50 or 100 steps, that memory footprint explodes.
And when it explodes, the AI suffers from something called attention dilution. It gets so bogged down reading its own massive internal dialogue of critiques and graph updates that it starts forgetting the initial constraints of the task.
This raises an important question for the entire field of artificial intelligence regarding deployment. Is a slower, more power-hungry AI actually worth it if it gets confused on ultra-long tasks?
Well, the researchers conclude that it depends entirely on the stakes of the environment. If you are just using an AI chatbot to brainstorm ideas for a marketing email or generate a quick recipe, a fast, cheap, hallucination-prone model is fine. If it makes a mistake, you just hit generate again. But look at high-stakes scenarios. Imagine an AI agent executing live financial transactions, modifying critical enterprise databases, or controlling physical robotics in a surgical theater.
Yeah, you definitely do not want the surgical robot arm operating at 1.2 seconds if it means it might accidentally slap a dirty sponge onto the sterile tray because it didn't check its work. You gladly wait the 2.15 seconds for it to pause, mathematically evaluate the safety of the action, and wash the sponge first.
Exactly. The latency is the unavoidable price of reliability. In environments where a single mistake breaks the system permanently, a slow, computationally expensive, but mathematically guaranteed safe action is infinitely superior.
To sum it all up for you listening, the era of AI acting like a reckless autocorrect seems to be ending. By fusing the creative, generative power of large language models with the strict mathematical reward systems of reinforcement learning, we're moving into a completely new paradigm. We are building systems that can construct spatial graph memory, plan over long horizons, and most importantly, critique and correct their own logic before making a physical mistake in the real world.
It represents the formal transition from a passive answering machine into an active, deliberate problem solver.
But before we go, I want to leave you with one final thought to ponder that goes beyond the data in this paper. We just spent this entire deep dive exploring how a single AI agent uses an internal critic to intercept and prevent its own bad ideas. But what happens in the near future when multiple RL agents are forced to collaborate on a complex, real-world task? Think about it. If two AI agents, both equipped with hyper-strict, uncompromising internal critics, are tasked with solving a problem together, do they achieve a perfect, flawless consensus? Or do they get trapped in an endless, hyper-logical argument, constantly vetoing and rejecting each other's proposed actions until the entire system just freezes up? If we give AI the ability to hesitate, we might just invent the AI equivalent of overthinking. Thanks for joining us on this deep dive. Next time your phone autocorrects you to a ravioli, just remember your pocket AI is still stuck in System 1. Keep questioning the world around you.